Hello, everyone. So we are going to talk about phases of matter and energy. So a lot of these words are things you've heard before, but we want to make sure that you've got all of the details that you need about them. So first, we're going to review the two types of energy. We have kinetic energy and potential energy. And so think about this diagram right here of this person riding the bike up the hill. When they're going up the hill, they're moving up the hill, and it takes energy to push that bicycle up the hill. That's kinetic energy because it takes energy for them to move. When they get to the top of the hill, they're going to be really tired, and so when they stop moving, then they have potential energy. So that means there's energy that could potentially do something, but it's not doing anything right now because the person has stopped moving. And then when they go down the hill, they're moving again, and that is energy being released because it's just so easy to go down that hill, but there's kinetic energy coming out. So it takes kinetic energy when you're moving, and the potential energy is when they pause because they're not doing anything, but they potentially could. So kinetic energy is the energy that is from movement, right, when they're moving up or down the hill. And then potential energy is the energy from position. It's stored energy. It could potentially do something, but it isn't right now, okay? Now, the reason that we care about energy is the particles, like the atoms we've been talking about, they're actually always moving. And because we know moving means kinetic energy, that movement is actually the particles using kinetic energy. So we're actually going to look at some particles and watch what they do. So here are a whole bunch of particles, and I can see that they're moving. That means I know that they're using kinetic energy. But one of the things that happens is I could actually heat up those particles. And so down below I have some heat being added, and I notice that the temperature is going up. And as I heat those particles up, it changes what they're doing. They're still moving, but they start to move faster and faster and faster. So the more heat that I add, the hotter those particles get. They really start bouncing around and moving very, very quickly. Now, I could also do the opposite. I could cool those particles down. That would be taking heat away from those particles. And again, that's going to change how they move. So they're going to start to slow down as I take their kinetic energy, as I take their heat away. And so the colder and colder those particles get, the slower and slower they start to move. So we're going to put that together in our notes. And so we're going to say when temperature increases, so right when it got hotter, those particles started to move faster. And because we know that moving has to do with kinetic energy, that means the amount of kinetic moving energy was also increasing. Temperature increased, kinetic energy increased. Now, the opposite, when the temperature decreases, then the particles moved slower, right? So temperature goes down, the particles move slower. That means that the kinetic or moving energy is also decreasing. So we're going to look at these two pictures right here in your notes and put this together. So in this picture, see how the lines on those particles are short? That means that they're not moving a whole lot. That happens at a low temperature. So this is a bit of a colder, lower temperature. So we have slower moving particles. So low and slow. If the particles are moving slowly, that means that they have low kinetic energy. There's not a lot of movement going on. Now, if I look at the other picture, I have these really long lines, so these particles are really zooming around. That happens at a higher temperature where there is fast movement, right? The more kinetic energy that they have, the faster the particles can move around. Okay. All of this is going to start to matter for our phases of matter. And just to review, the three phases of matter are solid and liquid and gas. Now we're going to define them in two different ways. So we're going to say, are their properties definite or indefinite? So to review those words, if something is definite, like you definitely have a test, it is going to happen. I am not changing my mind. So definite means it does not change. You definitely have a test, sorry. Indefinite means the opposite. It can be changed, right? Maybe it'll happen, maybe it won't. It's indefinite. So we're going to define those three phases of matter with those words. So first we're going to look at some pictures. If I draw a solid, and I want you to draw these particles into your notes, notice that they're all touching and really packed together. So solid particles are very tightly packed. Notice that even when I put these solid particles inside of this bigger box, they held their own shape. The shape did not change, which means that it was a definite shape. No matter what container I put that solid in, it's going to have its own shape that it wants. The volume, meaning how much space it takes up, also does not change. I can't squish this solid to be any smaller than it already is. Now, because those particles are really tightly packed, they don't have very much space to move around, right? They're already all squished together. They're not moving very much, which means their energy is very low. They can't move a whole lot, so it's low kinetic energy. Now let's look at a liquid. So in a liquid, the particles are still touching, but there's a little more room between them, and they can kind of slide over each other and flow around. So they're loosely packed, but they are still touching in a liquid. Now, if I took this liquid and I poured it into a different container, the shape that those particles attain together would change. That means that it is an indefinite shape. I can change the shape of a liquid by putting it into a different container. The volume, however, is definite. It does not change. I can't squish more water into my water bottle to drink. I can't push it down. My water bottle will only hold a certain amount of water, and I cannot change the volume that it holds. Because these particles have a little bit more space between them, they can move a little bit more than in a solid. So we're just going to call that like a medium energy. It's a little more than a solid. Now let's talk about gas. These particles are everywhere. They go all over. They're not really touching each other. There's lots of space in between them. So gas particles just go everywhere and don't really touch each other. The shape of a gas can change, right? If the air is in one room versus another room, that gas will just fill up the room regardless of what shape it is. So that's an indefinite shape. The gas will fill up whatever container I put it in. We can also change the volume of a gas. If you've heard something called like compressed air, they take those gas particles and they squish them down to fit in a small container. That's also something like a scuba tank. They squish a whole bunch of air into that tank for the scuba divers to breathe. So I can change the volume of a gas. That means it is indefinite. Because there's room between them, I can squish those gas particles together and make their volume, or the space that they take up, change. These gas particles have a lot of space to move around, and so that means they do a lot of moving, which is a high kinetic energy. So when we put that all together and we think about their energy, on this scale, as we go from the left to the right, the temperature will increase. And remember, when temperature increases, particles are moving faster. That means their kinetic energy is increasing too. So over here on the left, I have low kinetic energy, and over here on the right, I have high kinetic energy. So the lowest kinetic energy would be the solid phase. The particles don't move very much. If I talk about the liquid phase, it's a little bit more. And then in the gas, the particles are really moving super fast because they have all that room. So they have the highest kinetic energy, okay? Now, in those samples, the particles might be moving at slightly different speeds, right? Maybe they're in a gas, they're all going fast, but some particles might be a little faster than others. So when we're measuring temperature, it's just an average of the kinetic energy of all of the particles in the sample. So if one gas particle is a little faster than the other, that's okay because it's all going to average out in the temperature. All right, that's it. Good job, guys.